Welcome you all for today's class. Today we are going to discuss about boundary layer theory. Boundary layer for laminar and turbulent flow. Turbulent and laminar boundary layer you can say. So what is boundary layer and what is significance of its importance in fluid machinery and all kinds of interaction where fluid with solid surface, whether it is a aerodynamic design of the aeroplane wings and turbine blades and fluid machinery everywhere, aerodynamic design of the car surface, outer surface, everywhere this concept of flow separation and boundary layer applied. It was Ludwig Prandtl who given concept of the boundary layer. He said, according to Ludwig Prandtl, so first what is a topic of discussion is a boundary layer, turbulent and laminar. Turbulent and laminar boundary layer. So it was Ludwig Prandtl. He is a great fluid scientist, great fluid scientist because his theory is turbulent boundary layer, Prandtl mixing length theory and Prandtl universal velocity distribution. All everywhere he given so many concepts which are very useful from practical point of view and from experimental point of view. His concept universal velocity distribution equation and Prandtl's mixing length theory is very accurate from the experimental point of view, from theoretical point of view, and from all practical point of view. He also given concept of turbulent and laminar boundary layer because in most of the cases we are describing this boundary layer for the open channel flow, for the flow over the flat surface. Open channel flow means fluid is not in confined channel, but it is moving stream fluid or some body immersed inside the fluid. For example, submarine or swim inside the water. And for aeroplanes or fluid machinery means a flow, different kinds of flow where whether solid body comes in contact with the stationary fluid or stationary fluid, moving fluid come in contact with the solid surface or both are moving. Everywhere when there is a contact of the fluid and the surface of the body, there is a layer which is dominated by the frictional resistance and viscosity of the fluid. So around this layer, fluid flow is not free surface flow. Fluid flow is not free, but this is a layer where fluid is stagnated. Means its velocity is dominated by the frictional resistance between the surface of the solid body and fluid, and in this zone of this boundary layer fluid is stagnant, means free velocity flow is different from the stagnated flow within the boundary. So that is known as a boundary layer. So boundary layer, within boundary layer which is affected by the surface in contact of the solid body, and in this layer fluid flow is not uniform flow, but it is dominated by the whether it is a Reynolds number of the incoming flow or whether it is a distance from surface to the fluid. So up to the maximum limit where the effect of the surface taking place, and if we draw we divide this zone from boundary, then it becomes a boundary layer. Boundary layer is concept where fluid flow is affected by the viscosity of the fluid and surface of the solid body. So let us describe it by the fluid flowing over the flat plate. Fluid flowing over the flat plate. So by taking example of the flat surface is kept in the open flow and fluid is flowing over the surface, plate is stationary, and how this boundary layer will form that we describe here. So let us take a surface. This is a plate. This is a solid surface. This is a solid surface. This is a solid surface. And incoming fluid is coming. Fluid is coming from this side. This is a free stream velocity. This is a free stream flow. U naught is a velocity of the free stream flow. U naught, free stream velocity. Free stream velocity. The flow is taking place along the x direction and y direction. So this U naught is a simply U naught. U is a you can say U is a U naught. Maximum velocity along the f direction. So what will happen here when flow will come in contact with the solid surface? What will happen here when fluid will come in contact with solid surface? As soon as it come, This is x equal to 0, and here moving along the x direction. This is direction x. So what will happen once the fluid will come in contact with this leading edge? This is leading edge and trailing edge. So just the fluid, we take another color for drawing this. So this will come in contact and starting fluid flow, starting major, because concept of no separation, and initially velocity is very small here, and as moving forward along the direction, here this is flow is up to this point, is laminar, totally laminar, and moving here from this point we take, if it is transition, because fluid velocity becoming higher and Reynolds number become more effective. So transition will take place in this region. Transition will take place in this region, and Reynolds number is going higher. So this is a start of turbulence here. This is 1 and this is 1, 2. This is transition zone. Transition. Suppose here Reynolds number is RE equal to 3.1 into 10 to power 5, and here 5.5 into 10 to power 5. Up to this region, if it is known as, because from laminar to turbulence will start in this region, and from up to this point the flow become totally turbulent. And now starting here turbulent flow, will turbulent flow region, and as we move forward, and this is the region where up to this point the flow is affected by this surface, and beyond this again flow become totally free surface. As flow is here you can say flow is free surface, so it is a free stream velocity. But within this boundary, both sides, because this is a mirror image, you can see it, we can draw here same boundary, because it is kept in a very wide moving fluid, and this plate is kept in within the fluid. So same boundary layer you can see here, and this one is a mirror image you can form here in this side, opposite side also. So how fluid will behave in this region? Here starting, and from here you again find flow is not completely turbulent. This is turbulent region, turbulent flow here, but still there is a sublaminar layer. This is a sublaminar layer where fluid is still laminar, sublaminar layer. This is a sublaminar sublaminar flow. So this is a very thin layer within which fluid flow is just laminar here. If you draw a flow profile here, what is the maximum thickness? How we can find out maximum thickness of boundary layer? So there is no any, because this layer is highly fixed here. There is no any clear-cut boundary where we can say flow is turbulent and free flow. So this is how we can achieve maximum thickness of, because this direction is y, we take y direction along this, and x direction is here. So if we draw flow profile here, we will find like this. This is a flow profile as we moving, I think, yes, as we moving above y direction, velocity is increasing, and here reaching up to this point. Suppose this is velocity u equal to 0.99 u naught, where velocity become 99% of the free stream velocity, because this curve is not parabolic, but as we moving along y direction, means thickness of the boundary layer is increasing. So where is, we can say, maximum thickness of this boundary layer we can reach? This is the maximum thickness of the boundary layer, where this is defined by del, thickness of the boundary layer del, and at this thickness velocity become 99% of the free stream velocity. That is because there is a clear-cut no boundary. That's why we have to set a parameter that 99% of free stream velocity reaches here at del, and that is known as a boundary layer thickness. How we define boundary layer? In that is a turbulent, because we find that in turbulent zone maximum thickness of boundary layer we can achieve at a distance x. This is distance x, where we get maximum thickness of the boundary layer del, where velocity within this boundary layer reaches 99%. Here, if it is stream limit at this point, here velocity becomes 99% of the free stream velocity, or we can say 1%. 1% of the asymptotically, because this curve is velocity profile curve is asymptotic. so reaches 1% of the asymptotic limit, or you can say velocity at this point reaches 99%, 0.99 value of the free stream velocity. You become 0.99 of the free stream velocity. At this point, thickness of boundary layer is defined del. This is the thickness of the boundary layer where velocity reaches 99% of the free stream velocity. So how we can define? We can define how behavior of the fluid, behavior of the flow, how fluid behave in this region. We see that as we're moving here from this point to this point, this point to this point, velocity is fully dominated by the viscosity of the fluid. Means due to frictional drag occurring between layer and between surface and the fluid, if velocities are not very high up to this point, flow is totally laminar, and velocity as fluid is approaching, we are reaching from this direction, fluid velocity is increasing. At this point, the Reynolds number becomes 3.18 10 to the power 5. Just turbulence started, and from this point to this point to 5.5 10 to the power 5, flow become totally turbulent. So this is known as a laminar transition zone. This is known as a transition zone. And from this transition, from when velocity reaches up to maximum, means Reynolds number reaches 5.5 into 10 to the power 5, flow becomes totally turbulent. And from this region, the flow becoming so layer of thickness, because here stresses becoming more and more dominant, and layer of the boundary layer also increasing and reaching maximum up to this point, and flow also become turbulent, totally turbulent. In turbulent region, we can find maximum. We can define the thickness of boundary, because in turbulent zone we get maximum thickness of the boundary layer, and this we define by using 99% value of the free stream velocity in turbulent zone. So this distance is x from the leading edge. So what is behavior of fluid here? One thing that we have to define, that in boundary layer, what are properties of fluid in boundary? What are properties of fluid and flow behavior in boundary layer? So first thing is that del u over del y does not zero, because in boundary layer region flow velocities are varying. You can see from here to here, everywhere in boundary layer region flow velocities are varying from u is 0 at the surface and reaching maximum at the boundary layer. So this y velocity is changing with the y direction. So del u or del y is not constant, but del u at del y from outside the boundary layer is constant, is 0, but not within the boundary layer it is 0. Number 2, we can define boundary layer thickness in turbulent region and laminar region. If we draw a graph between u upon u naught and y upon del, this is the maximum limit will be 1 and 1. So this one is a laminar profile, and this one is a turbulent profile. Laminar and turbulent flow profile. Laminar and turbulent are different in laminar region, and because if we draw the y upon del, means as we moving along y direction, velocity is also increasing. So y by del reaches maximum 1, and u by u naught also reaching maximum 1. So this profile, if you draw, you can see this one is a more steep. If you draw that, take one point here at this point. So this is a maximum velocity, and you can see del y here, del y and del y are same. You can see from this graph that del u over del y is greater for the turbulent than del u over del y for the laminar from this graph, because you see that delta u here and delta y for turbulent is less compared to delta y for the laminar, because see this one is greater than this one. So delta y for laminar is more than delta y for turbulent. So this del u over del y for turbulent is higher than del u by del y for the laminar. So velocity gradient for turbulent is more steep compared to velocity gradient for the laminar. So this is very important information. You can see here by this graph. Another thing we discussed that how wall resistance, wall stresses varying. We will draw a graph for wall resistance from transition zone. This is a transition zone and laminar zone, transition zone. This is a laminar zone, laminar, and transition, and this is a turbulent zone. This is a turbulent zone, and this is a tau, shear stress, wall shear stress. We draw a graph like this. This is a graph for the. This is a graph. As fluid is moving from here to here, starting in laminar zone, shear stresses are reducing because of the Reynolds flow velocities are dominating over the shear stresses. So shear stresses is reducing because of the flow velocities are higher for a higher Reynolds number. As reaching turbulent transition, again transition is not very dominant, so stresses are not very high, again dropping. But as we reaching turbulent region, so in turbulent shear stress also become very significant. That's why as we moving past from the turbulence zone, in turbulence zone, shear stresses again, wall shear stresses now again increasing because this wall shear stresses is come due to laminar plus turbulent, contributed by the laminar and turbulent. So shear stress increases in turbulent zone because of the turbulence. There are two types of the laminar shear stress and turbulence between movement of layer between two zones, higher velocity, lower velocity, high velocity. Fluid particle will move and turbulence is created, and due to this turbulent shear stress becoming dominant. So again, shear stress increasing in turbulent zone. So this is all about how boundary layer will form and what are parameters which affect boundary layer. Leading in velocity of approach means approach Reynolds number and surface and viscosity of the fluid and nature of the surface. If surface is highly rough, then turbulence also increases due to roughness of the surface also. But here, due to flow velocities, two more important factors are there: flow velocities and viscosity, which are dominating factor which contribute in formation of this boundary layer. And boundary layer thickness is defined where from x distance from the leading edge, where velocity reaches 99% of the free stream velocity, and that thickness is known as a boundary layer thickness. And due to this boundary layer formation, flow is stagnated within the boundary layer, and it will have means this boundary layer, due to this boundary layer, fluid is shifted away the boundary layer, because in absence of this surface, fluid would have been flowing in maximum velocity, that is u naught. But due to this boundary layer, fluid is not flowing in full capacity within this boundary layer, so fluid is shifted. On that basis, we have to define what is a